Welcome back to ECE 442-542. I feel like I'm missing something, but if you are in 542, you have your project due by 11:59 tonight. The TCE forms are due tonight by 11:59 p.m., and I really would appreciate you filling that out. And I don't, So they were suggesting different ways of getting you to follow through on filling out your TCEs. The easier one might be to give you extra credit. No, that's
We have one price.
yeah, the one the next item on the announcement is concerning the final exam, which is not optional, unfortunately. It's not extra credit, and there is review material that's already on D2L. There's an additional lecture. Monday we had lecture 8.2. Today is 8.4. Somewhere between, in 2014, we had lecture 8.3. So there's an example of how you might be able to use full state feedback for your homework in terms of a physical example using MATLAB. There are some additional office hours that are not consistent with the normal semester's office hours. Our final exam is on the last day of finals. So I have, Thursday, Friday, Monday, Tuesday, every day before that, an opportunity to be at office hours. I apologize that some of these might be during one of your final exams, but hopefully if you do have questions, you can get those answered either via office hours or via email. There is one office hour prior to homework number 8 being due. Homework number 8 is extra credit. Extra credit is really just, if you consider 80 points for your entire and scale that up to 100, then 1/8 of that is the extra credit, depending on whether you're in 542 or 442. So it's basically an additional homework assignment in extra credit points. So it's a fair amount of extra credit. Even though it's extra credit, the material will be on the final. So if you don't do it prior to tomorrow night, I would recommend that you understand how to do it prior to the final. And the final exam is in red. Hopefully you don't miss this. This is on Thursday, not tomorrow, but a week from tomorrow, and it's at 1 o'clock to 3 o'clock in this room. So it's a little different than normal. It's now 2 hours instead of 75 minutes. Today what I want to do is explain a little bit about what that final might look like, not too much. You'll get some final review material on D2L, and then we have a long list of things I want to go over or talk about in today's class. But the first thing will be to give you the information about the final exam process, and then we'll get back into this last unit of material, which is state space design. And there's many different block diagrams associated with state space design, and I hope if you're a visual learner that might make some sense to you, or it might help make it a little bit more clear than just showing you the equations. I could give you the equations in linear algebra terms or in dynamic terms, but you can also obtain those from the different block diagrams. And I was just going to have different dashes, but I thought then they can't numerically determine how many block diagrams we have. So I did them A, B, C, all the way up to F. And how many is that? 6, I think. Isn't H 8? I don't know. 1, 2, 3, 4, 5, yes. F is 6. Thank you. So 6 now is our magic number. That's true. But you could have said 2 times 3, I guess, as far as the number for F. State space representation, what does that look like in terms of a block diagram? in contrast to maybe this transfer function. Now you're essentially looking under the hood of G of S, and you're seeing it as a state space representation or a discrete time dynamic system. Full state feedback without a reference input, I'm going to say is a regulator, as opposed to item C, which is full state feedback with a non-zero reference input. Now we have an R of L that we're injecting, and we may want to track that, so that we might put R of L at 2, then we might put it to 4.5, and then we might put it to -3, and we want our system to track that. That's what I mean by full state feedback with non-zero reference input. We can also start to combine these concepts of time domain block diagrams and transform-based systems when we have this integral control. Meaning, is it possible to pair up full state feedback with this integral control concept? We learned that we like PID controllers. They're our friend. Why? The integral allows us to track things very robustly with zero steady state error if it's a constant, if the closed loop system is stable. We can do the same thing using full state feedback design techniques. We can introduce an integrator, and that's actually where we will spend the majority of our writing today. A lot of it will be just showing you pictures of these block diagrams. The last 2 of the 6 block diagrams deal with falling over. Sorry, it's already happy hour. That's true. Happy hour has already begun. And I'm now kicking the table, not even knowing. So now it's shaking. So in E and F, what we're doing is we're trying to use just the output signal and the input to recreate or estimate what these state variables are. In these first 4, we've assumed we can go inside under the hood and access all of our state variables. In the last 2, in E and F, we're saying, can you, with just the output and the input waveform or signals, recreate or estimate these maybe 6 state variables? That's what we want to do with E. Just create an estimator, and those estimators are going to be X hat, estimates of our state vector components. And then F is, if it's a good estimator, can we use those estimated values with our full state feedback gain matrix to basically create this closed loop control configuration using state space based design approaches? We probably won't get there, but you can actually decompose that design process into 2 separate stages. You can find the full state feedback gain matrix, and then separately or independently you can find the estimator gain, similarly to how we found the full state feedback gain, and you can combine those to complete step number F. That's beyond the final exam, but I want you to be aware of that it is possible. As I said, what we want to do after we look at those block diagrams is work through where does this integral control come from, or how can we create this integral controller, and we'll derive, now we will add that on to our state space representation. We'll augment the matrices. The phi, the gamma, the h, and the j. We'll add rows and columns to those. That's what I mean by augment. And then we will discuss how we can use those augmented matrices to come up with a design that's consistent with what we've already done with full state feedback design. And we'll just have to figure out how do we extract the appropriate elements in that augmented full state feedback gain matrix. I don't think we will get here, but this is where I would like to go, or this is the next logical step in the process of filling in these A through F. Full state estimator, develop the equations. If I show you the block diagram, you can actually write down the equations from the block diagram. And then we would go about looking at selecting the estimator dynamics. Where do we locate those? So now we have closed loop dynamics, and we also have estimator dynamics, and those two are decoupled. But what we want to do, or what we would want to do, is make sure that our estimates are accurate and then use those to drive the system. And if that's the case, we actually want our estimator dynamics to be faster than the full state feedback dynamics. More than you wanted to know, but that's where you can go with this information or with these techniques. And the last one is really concerned with block diagram number F. That's called a full order estimator. Now, if you had 10 state variables, you can build an estimator that's 10th order that will allow you to estimate all 10 of those states, and then you have a full state feedback gain matrix that's 1 tall and 10 columns wide to manipulate or adjust, scale those estimated state vectors and feed those back to give us a full order compensator. Let's jump back. Well, actually, we're jumping ahead, what, 8 days to next Thursday, the final exam. It is comprehensive, and there will be 15 questions. So the 75-minute exam, there were 4 questions. No, 5, but each kind of had 2 parts, so there were 10. Now I'm increasing the length of time to 120 minutes instead of 75, but I'm giving you 15 questions. And I always kid you that maybe the first question, they all hinge on your right answer to the first question, and then I only have to grade the first one if you get it wrong. And problems 2 through 15 are automatically wrong if you get, it's not designed that way, okay? That's not the way I want to create the final, but you could sort of see how I could do that. I could make this a staged question or staged questions so that you can follow through the design process. And I want you to be comfortable doing that no matter what I give you in terms of a question. This should look the same, except now you have one more sheet of notes. So now you have 4 sheets of notes. You can bring 3, a maximum of 4, plus the Laplace and Z transform tables, and that can be up to 2 tables or 2 pages worth. You can bring all sorts of drafting material, a protractor, a ruler, a straight edge, a compass. Just don't harm yourself or your neighbor with these sharp instruments, okay, if you bring one. And you can keep your other instruments concealed. A graphing calculator is allowed, closed notes, closed book, no computer, and no cell phone. And as I said, the material to prepare you for the final is already on D2L. There's a little unit at the very bottom of the content page that says, here is the final exam material. It has notes and a video to get you up to speed or reviewing the material for the final exam. Are there questions on the final exam process? Not what will be on the final. What will be on the final, it's comprehensive. So hopefully there you have all of this material from previous exams. That's fair game for the final. Let's start looking at block diagrams. So now I show you equations. Here is the first set of equations. We have Nevada, Michigan, and another state, the 51st state, the Q state, to worry about. Meaning we have Nevada state variable components, n, that's the size of phi, that's n by n, it's square. Gamma is n rows tall, Nevada tall, and Michigan columns wide. What do we typically have for Michigan in terms of how many columns are usually in gamma? 1. So I was afraid somebody was going to say 4, and I'm going to say, oh, that really opens up the possibility. But we probably will stick to 1 for this class. And Q, what in the world am I doing? Are you guys going to wake me up? How many times have I done this wrong? Oh, that's okay. What am I? Wow. So Y is possibly Q rows tall, but typically what will it be? 1. So usually we have a scalar output. And if Y is Q by 1, what is H dimensionally? Let's say Q is 2 and N is 10. What's the shape of H? Q is 2. You should be able to visualize or just sketch the shape. Is it square? H. You know H is not square. Is it a short, wide rectangle, or is it a tall, narrow rectangle? H. What are its dimensions? And you can look at this equation to figure that out. You know Y has 2 rows. X has 10, what did I say, 10? H has 10 rows. So what's H have to be? To be compatible with that equation, meaning for that equation to be valid, H has to have how many rows? The same number as you have rows in Y, which is 2. So you now know H is 2 rows tall and how wide? 10. It has to have 10 columns so that each of those columns can be combined with each of the 10 rows in X. So H is 2 by 10. If you go to, never mind, Home Depot and ask for an H matrix, they would pull out a 2 by 10. Sorry. It's going to be an interesting lecture tonight. Here is our block diagram that simply creates that system of equations above in a block diagram form, meaning the delay is a bank of delays. And if X is 10, how many delay elements do you have? If X is Nevada tall and 1 column wide, how big is the bank of delay elements? How many delay elements exist to give you, if you put in X at time L plus 1 and you want X at time L, you want 10 of those to happen. So you need 10 delay elements in that box, and that's what's somewhat buried. Yes? So the 10 delay elements you now have in parallel, they're now stacked so that X sub 1 has its own delay element, X sub 2 has its delay element. They all then, you're measuring X1, X2 through X10 and feeding that into the system matrix phi, which is 10 by 10. So you have a 10 by 10 multiplying a 10 by 1, that produces a 10 by 1 that now gets added in to form a 10 by 1 matrix X of L plus 1. You could then, by being given this block diagram, you can write down the above equations, governing equations. They are related. And if you wanted to, you could take that time domain description of your system with the arguments of L, that's in the time domain, and take them into the frequency domain. Z-transform them. If you Z-transform little x of L plus 1, what's that look like in the frequency domain? An advance of 1 does what with an operator? Or what operation is required? It's already there on the board. You're just multiplying by z, right? Z is an operator, and z by itself corresponds to an advance of 1. Z to the minus 1 is a unit delay. In this case, if we z-transform that dynamic equation, we have z times capital X of z, and we can put in that identity matrix as a placeholder if we want, which we do in the next line, but then we have phi x of z plus gamma u of z. Maybe I should have capitalized u, but it's in the frequency domain because the argument is z, and then we can z-transform the output equation, y of z is equal to h x of z. From the dynamic equation, we can factor out the common z-transform state vector, capital X of z. We can hit both sides on the left with zi minus phi inverse, and now we have x is equal to zi minus phi inverse gamma times u of z, which when combined with the output relationship, hx, allows us now to derive maybe one of our cheers. I don't know if we had too many cheers in this class or not. Not enough? So now we have an additional one. Oh, and I forgot my pom-poms. Good. So now we have g of z. The transfer function is now h times zi minus phi inverse gamma. And in this particular representation, we did not have a direct feed through from the input to the output, but you could, and that would just make one more connection in that description. This is now a way to connect the transform base analysis or techniques that we've been playing with this semester with the state space, and you should be able to obtain capital G from the state space matrices, or if you are given a G of Z, can you extract or create a state space representation? And I say a state space representation because those are not unique. We could have 100 different state space representations and still produce the same G of Z. This connection, though, allows you to see that the poles of G of Z correspond to the eigenvalues of your system matrix phi. That's where that connection is visible from, that relationship. If we now want to manipulate the dynamic behavior, maybe we are not happy with phi, the original open loop eigenvalues, then we can go in under the hood. We're not measuring the output y. We're saying we can actually go into the system and measure each of the state variables. We can measure position, velocity, voltage, current, whatever is in our state vector, weight those or scale those and use that to create the input matrix U of L. Or I'm sorry, the input signal U of L. U of L is now minus K X of L. And K is a matrix in general. If X I'm waiting for the pound on the wall. She's late, isn't she? Maybe she only does that on Mondays. Pardon? Oh, it's the last day of class. Well, she's getting ready for the mid-intercession, right? Sorry, I'm searching for content. But here is our full state feedback gain block diagram. That was the regulator problem. We didn't have an external input. We didn't have an R of L. If we want to make that system with full state feedback still track a reference input, if we want to say, oh, set our speed, our cruise control to 45, then you say, let me switch it to 55. Oh, let me switch it to 65. You want to get up and lock on to that speed, and that's now your R. What we've learned in last time, and this is basically homework number 8, how to select K and N sub 1. In our particular case, U of L if it's scalar, and R of L if it's scalar, if they're both 1 by 1, what's the dimension on capital N sub 1? Last year. It's 1 by 1, isn't it? It's a scalar. Capital N sub 1 is a scalar. It's a 1 by 1 matrix. K, if you had 4 state variables, if little x of L was 4, and we still had 1 input for U, what are the dimensions on K? What's the size of K? K is compatible with U and with X. So K has to produce as an output something that's the size of U and U. I'm sorry. U of L. That's the size that you want the output of K. So it has to be 1 row tall. How wide is K? It has to be the number of columns for K has to be consistent with the number of rows in X. So K is this long, or I should say short, wide matrix. I'm saying that because a lot of times on these finals, students stack those in a column vector for K, and that cost you some points, and I don't want you to lose any points on the final exam. What did we say? We said if I give you a block diagram, you should be able to write down the equations that are governing that system's behavior. Do you see where the top row or the top line can be written down by inspection of the block diagram? Meaning your crib sheet, you could sketch this block diagram, and if you had to, you could now derive the equations that are related to that block diagram. Little x at time L plus 1 is at the second summing junction. That's the output of that second summing junction, and you need that to equal the inputs to that summing junction. Meaning U of L, or we now have gamma scaling what's forming little U of L. And U of L has 2 pieces. It has N sub 1 times R of L, and it has minus K times X of L. And that's what's in blue in that first line. We also have the inner loop, which is the open loop dynamics. We have X of L plus 1 also has a piece associated with the system dynamics phi times X of L. And now we can simply combine like terms. We can factor out the state vector, little x of L, and we now have a closed loop system matrix. Or K is designed, this full state feedback gain matrix K is designed to adjust the dynamics of our open loop system. And when can you do that arbitrarily? If you remember what we talked about on Monday, there was a concept that we said if our system is blank, we can use K to move our open loop eigenvalues to any location we want for the closed loop eigenvalues. Did anybody record Monday's lecture? Did you watch the recording or listen to the recording? Oh, don't do it now. I don't know what time it was in Monday's class, but what were we talking about? What was the concept? Controllability, right? So if our system is controllable, then we can find a K to position the closed loop eigenvalues, which are the poles of our closed loop system. We can now make phi sub c have eigenvalues where we want. And you know where we want those eigenvalues, right? We have a heart, which is percent overshoot. We have a target. Well, a unit circle we want to be collapsing, right? So we have these concentric circles. The smaller the circle, the faster our system responds. So that's settling time for the circle. And then we have wedges, which give us time to peak. We know how to translate those performance specifications into closed loop pole locations, desired dominant poles. And that's maybe what we would use to determine eigenvalues for capital phi sub c. Are hearts, circles, and wedges. I'm getting hungry. I thought that was a breakfast commercial. But I didn't associate colors with those shapes, did I? Red hearts, blue circles, I don't know. Orange wedges. Oh, now we have orange slices. But once we do that, now we can find the closed loop transfer function for that block diagram in terms of the system matrices. Similarly to what we had done before. We have y is now h times zi minus phi sub c inverse times in gamma n sub 1. And if we want, we could remind ourselves of what is associated with or what makes up this closed loop system matrix phi sub c. That's phi minus gamma k. Or, written more compactly, we now know that the output z transform, y of z, is t sub c of z times r of z. And if we're viewing this as a tracking problem, what do we typically want t sub c of z to exhibit? What property do we want t sub c of z to possess? You want t sub c, that's our closed loop transfer function. The very first thing you probably want is for that to be stable. You know where you might want those dominant poles. That's the heart, circle, and wedge. Based on those performance specs, you can now specify where you want the dominant poles. Where might you want the other poles? If you had 4 poles and you said, oh, I want the dominant behavior to be influenced by those 2 dominant poles, those are the slowest poles, but they're going to be specified by the performance specs. Where do you want those other 2 poles? Or where's a convenient location to locate those 2 remaining closed loop poles? At the origin. Probably give those values of z equal to 0. So now you have a second order that has your dominant poles, and you multiply that by z squared. Now you have a fourth order polynomial. You can use that fourth order polynomial to specify k, the closed loop system, the full state feedback gain matrix. Not only do we want the closed loop system transfer function to be stable, or our closed loop poles to be inside the unit circle, we may want to manipulate the DC gain. Why is it important to have the DC gain a value of 1? Oh, I am going to be deadbeat if I'm not careful. Why do we want a DC gain of 1? How could you explain that? I think you've all answered that except for 2 students. So now you all know where the DC gain needs to be, right? Or why we want it to be 1. Why do we want it to be 1? And how do we make it equal 1? That's already on the screen, is it not? How do we make our closed loop transfer function T sub C of Z have a DC gain of 1 for this part of the class? How do we make that happen? That's how we pick n sub 1. We select n sub 1 to give us a DC gain of 1. How do we find the DC gain of capital T sub C of Z? How do we find DC? 0 frequency in the discrete time case. Z is equal to 1. So we evaluate T sub C of Z at Z equal 1, and we hopefully only now have one more unknown, and that's n sub 1, and we make that n sub 1 selection to make that entire thing have a value of 1. We do that so that we can have tracking behavior. If I put in a 2, I get out a 2 if my DC gain is 1. If I put in a constant of 5, then after the transients, and what influences the transient behavior? The closed loop poles. That's why you've picked the closed loop poles. You want those closed loop poles to give you the behavior, the closed loop behavior that you want. And now when you set that reference value to 2, you have the transient governed by the closed loop poles to get to 2. Then if you change that reference set point to 7, you're going to go to 7. How? If your closed loop system is stable and you have the desired dynamics that you want, which are influenced by the closed loop poles. And this is the formula that you could have on your 4th sheet of notes. For a single input, single output system with 1 control and 1 output, that's the SISO, H times ZI minus phi sub C inverse. Oh, and how have I messed up here? We want the DC gain to be used to select n sub 1, and so we are evaluating that when Z is equal to 1. Or we now have I minus phi sub C, that quantity inverted, times H pre-multiplying and gamma post-multiplying. And that will just be a number. That will be a scalar. H, I minus phi sub C inverse times gamma. You should be ready to invert a 10 by 10 matrix on the final. 20 by 20? Okay, I'll give Nick a 20 by 20. I maybe have a 20. I don't know if I have 20 of those. What if we didn't know very accurately our system matrix phi, our input matrix gamma, and our output matrix H, but we still want to have nice tracking behavior? You go, well, I remember when we were doing the transform design, we would put an integrator in make an integrator for our controller. We would have a PI controller. To force an integrator into that, we would now augment our block diagram to have or possess an integrator. And how did we do that in the past? Well, we just put a pole in our forward path at 1, at Z equal to 1. And we can do that with this 1 over Z minus 1 factor. That's an integrator. We need to scale that particular signal, and we'll call that K sub I. That's basically our integrator gain. But we're still allowing us to go under the hood and manipulate all of the state variables with full state feedback. We'll call this a K hat just to distinguish it from K. The question now was, I have several different ways that I'm pulling off information or signals from my system. One is I'm taking my output, and in order to be tracking, typically I want to compare the output where I want to go with my input R. And that's happening via the comparison of R with Y. Coming out of that summing junction is the error or the difference between Y and R. Since E is, in this case, the way I'm drawing it, is now Y minus R. That allows me to put this minus sign in here for minus K sub I. Meaning, to drive the integrator, I just want that input to the integrator to be the error that I'm trying to force to be equal to 0. And that error is the error in the output, the difference between Y and the reference input R. But I'm still assuming that I have full state feedback, which means I can go in and access the full state feedback gain matrix, the full state vector X, and feed that through a full state feedback gain matrix. And that now comes in to create part of the input U that's being used to drive the dynamic behavior of my system. U now is made up of a state feedback component, that's minus K hat X, and it also is made up of an integrator component, minus K sub I, X sub I. And I have two different feedback paths in that block diagram. I have one feedback path. How many lines are in the blue highlight? This could be a final exam question. It should be an easy question if I gave it to you. So hopefully that was not picked up on the microphone. But how many lines do I have from X to K hat? So I've heard a 3, I've heard a 4. Do I have any more? I guess I'm at an auction. Turkey leg? Okay, we don't have a turkey leg, but now if I didn't tell you how many state variable components, any of these answers could be correct. If I said we had 3 state variables, the 3 would have been correct. If I said we had 4 state variables, the 4 would have been correct. If I said Nevada state variables of 10, then this line right here would actually be containing 10 different lines. They're all bundled into a cable that has 10 signals going through it. Oh. Okay, and now, how many signals are in the yellow highlight? And I don't want to pick up another 10 cable. How many are in the yellow highlight? 3. When would 3 be the correct answer? When you have 3 outputs. What do we typically have in this class? How many output variables? 1. In this case, if Y represented one output signal, we're feeding one signal back to compare with R. And R is now a scalar input. These lines, then, that are in this diagram are abstracting away a fair amount of information. The blue line is 10 lines in amount. The yellow line is 1. Question? So now what happens if y and r are not the same dimension? Then you have a problem. What you could, typically, the number of reference signals that you have will match the number of outputs. Or what you could do is you could say, you know what, I do have 4 outputs, but I really only want to track 1. So you could just pick off one of those outputs and say, this is the output that I really want to track with respect to. Or you could say, I need to track 2 different outputs, and now you have 2 lines, and you have 2 independent inputs that you're applying. But in this particular configuration, we are assuming that R and Y are compatible. They create this error signal E as the output to that summing junction. Other questions? And here I'm just making a point that the control signal in the time domain has 2 pieces. One piece is made up of the states. That's the minus k hat x of L. And the other piece is made up of the integral signal coming out of the integrator. And what are you integrating? You're integrating the error. So if this system is closed loop stable, you're forcing that error signal to go to 0. Now, you might say, well, that's well and good, but I can't get in under the hood and have access to all of my state variables. So why did we study all of this full state feedback design? Don't get too upset. Now I'm going to tell you a way out. Now I'm going to say that we can actually estimate those states, x of L, by simply knowing what y of L is, the output, and what the input is, u of L. And how are we going to do that? We're gonna do it with some brain power, aren't we? How do you make a copy? Control C. Or old school, you might go into the office and get the photocopy machine and make a copy there. Old school is you write it down twice. Well, that's exactly what I've done. Do you see a duplication of the original system in the bottom? You have gamma, you have the same delay, you have the same phi, and you have the same output matrix. Don't look at the blue stuff just yet. But do you see that I've basically copied the upper block diagram with the lower? What I will highlight in yellow is, let's say, the original system. This would be our plant. That you're comfortable with. What have I done in addition to that? Well, I've said, you know what? If we could start everything at the same initial condition, I should be able to produce Y by just copying what I know to be the original system. If I know my system well enough, and I know the system matrix phi, I know the input matrix gamma, and I know the output matrix H, can't I just build a copy? And then inject the same input into that copied original system. The problem is we may not be starting at the same location. Somebody might disturb the original system, or we may actually not know very accurately phi, h, and gamma. If we don't, then we try to compare the 2 outputs. The top one is the actual output y. The bottom one is the estimated output, which I'm putting a party hat on. You've got to stick with me if you want to party. So now this y has a hat on, right? That's the estimate of the output y. So we compare the plant's output with the estimated output, and they may be different. If they're different, then there's an error signal, E sub y. We use that error signal to adjust the behavior of our estimated state. Meaning, now what we have freedom to do is we have freedom to select this estimator gain, L sub p. And we use that to control or adjust the dynamics of our estimator. The dynamics of the estimator are how fast do you want x hat to approach x? You probably want that to happen fairly quick relative to your closed loop dynamics. And you're doing that by comparing y, the actual system output, with the estimated output y hat. So now the question was, how does this allow us to not be able to look under the hood? We're actually saying we can look under the hood, we just can't, it's too hot. We can't touch things under the hood. So we can't access X of L. But we're assuming that we know what's going on under the hood. We know the dynamic behavior. So we're assuming we know fairly well the system matrix phi, the input matrix gamma, and the output matrix H. We're assuming we know that, so we've now built a copy. We know that the system may be getting kicked, and our estimator is not getting kicked in the same way, so that y might be different than y hat. And because those are different, we use that information to inform or adjust the estimate of our state x. X hat, if this system, now we want our system not only to be controllable, but we want it to be observable. We're not going to go there, but these are topics that you will pursue when you go to your next class in graduate school. Don't fall over, but in graduate school, you'll now be learning, and you may want to show up on time in graduate school so that you don't miss out on the information. Okay? But what we're doing now is, if our system is observable, then we can control the estimator dynamics by the choice of L sub p. We can carry, now that I've lost the entire class, we can carry this one step further. We can create the estimator, and now if we don't have access under the hood, if we can't touch the states, if we can't touch X, we can definitely touch X hat. We've built that. That's in our possession. We have this estimator down below. We can now, if X hat is doing a good job of estimating X, we can now use X hat as if it were the true states, and use the full state feedback gain matrix K to adjust the closed loop dynamics. Now we can, yes. What are we assuming? Now we are assuming that this is all buried in our system, although we know the behavior, or we can have a good feel for what the system looks like in the matrix phi, the input matrix gamma, and the output matrix H. And we now have access to the input U, that's one signal, and the output Y. But once we have access to those, we can now build everything else below or outside of the yellow to create this controller. And in fact, what we would be comparing is we would be comparing what's outside the yellow to maybe a PID controller. How does this compare to our transfer function based design approaches? where are the poles, where are the zeros. This is now in the feedback path, but you can start to get a sense of how do you compare these different control strategies or these different control techniques. So we're building a separate system that's supposed to mimic the true system. We're using that to estimate the true states and using those estimated states to inform or to control the system that's creating the input U of L signal to the system. So now what's the benefit of doing this versus building a system that maybe behaves the way we want to begin with? A lot of times you don't have that flexibility, but if you can get in the same room with the original design team that's building the system, you probably want to have a fair amount to say about phi, gamma, and h. It would be nice if you could inform where your zeros are, because we now know how zeros influence or impact the design approach and how those are interconnected or related to the system matrix phi or the open loop eigenvalues. The other thing is a lot of times you may actually want to mechanically design a system that's naturally unstable, meaning a fighter aircraft. Maybe you want it to be naturally unstable so that you have a lot more ability to maneuver that, but you definitely have to control it, or otherwise you couldn't fly the plane. So the top part could be a mechanical, it could be an electrical, it could be a thermal, it could be an electromechanical. The top part is something that you've now been paid to try to adjust. And this is just one control strategy that you can start to examine to maybe say, is this what I want to do in terms of controlling the system? Let's now talk or work through this idea of integral control. Now we're going back a few steps, maybe to the fourth step, where we're incorporating or putting in an integrator into the original system that we maybe want to control using full state feedback techniques or strategies. Here's our basic block diagram, and you can see that the original system is still there. That's our original system with the system matrix phi, the input matrix gamma, and the output matrix h. And now the delay block, I'm just labeling in the frequency domain to be z to the minus 1, where z to the minus 1 might actually be a bank of delays. If phi, if the system matrix is 10 by 10, then how many z inverses do you have? I have quite a few z inverses in this class. Z inverse usually is z, 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 right? Don't you have? So I have most of you are awake. You're z inversed, right? So we have 10 of those in this case. Ooh, the rest of you, the remaining 90 are asleep. Okay, let's not talk about that. Oh, you're one time, you've advanced. You're beyond this point in the lecture. Thank you. So now we have our system highlighted in yellow. We have the full state feedback gain, and we said, let's now compare the output to a reference to create an error and integrate that error. What we want to be able to do now is figure out how do I pick k hat and k sub I. That's what you want to be able to design. Or you're now saying to implement this strategy, in order to implement this integral control structure requires us to determine these values for the gains, k sub I and k hat. So let's see if we can actually figure out what these equations need to be. We're, I hope, comfortable with how to interrelate phi, gamma, and h. Now we need to say, how do we introduce an additional state, maybe x sub I, into this formulation? We have it in a block diagram. What we want to do now is figure out how do we describe the dynamics of x sub L in terms of y and r in the time domain. We have it here in the block diagram. Let's just see if we can extract that. And in a sense, this is a good review of some of the material we've learned in this class. We're now going from the block diagram description into the time domain, where in this case the block diagram is in the frequency domain. What are the dynamics? We have our integral term, where we had our air signal. We had that pole at z equal to 1, so that's this z minus 1 factor in the denominator, and that produced an x sub I. This should be a given if this was on the final exam. What is x sub I of z equal to based on that block diagram? It's the transfer function of that set of dynamics, which in this case is 1 over z minus 1 times the input, which is E of z. Or if we now take that and cross multiply the numerator and denominator factors, we have z minus 1 times capital X sub I of z is equal to E of z. What's this look like in the time domain? This is now the frequency domain description of this dynamic relationship. What is z times capital X sub I of z in the time domain? Z is just an advance operator. You told me the difference between z and z inverse before, right? So this is now x sub I of L plus 1. And let me put that next capital X sub I on the right-hand side of the equality sign and take it into the time domain. And what does it produce? That's trivial. And then we have plus E of L. But what's E of L in this particular system? What's the air signal from this block diagram? How did we define the air? The air is the output of that summing junction. What's the equation for E? It has to be equal to the inputs to that summing junction, which is now Y minus R. Meaning we can now rewrite E, or recall, E of L was just Y of L minus R of L. But Y of L can be related to the state vector. Y is H times X. minus R of L. So that now we actually have an additional set of dynamic equations due to that integrator piece that we added on to that original system. We can now say that x sub I at time L plus 1 is equal to x sub I of L plus h x of L minus R of L. That's the dynamics due to that additional set of block and summation or summing junction that we put into our system, and this piece is just the error signal. How big is this x sub I vector? How tall is it? How many rows are in x sub I of L? Who moved this table anyway? I keep tripping over. How tall is x sub I of L? How many inputs do we typically have? How many outputs do we have? Can you back out that information? What's the size of H? Suppose you had 4 state variables or 4 components to your state vector. So X is 4 tall, 4 rows tall. And how many outputs are we assuming typically in this class? 1. So what's the dimension on H? It's 1 row tall and 4 columns wide. If H has 1 row and it has to be compatible with the rest of this equation, how tall is x sub I of L? Or how tall is x sub I of L plus 1? It's not the average human height. It's in integer values. And it's this tall, right? Actually, it's this tall. It's 1 row tall, right? H was 1 row high, and that's supposed to be consistent with this. So x sub I is just one more state variable. We want to now augment that onto our original system description. That's what I'm doing now. I'm going to say, let's augment the integral dynamics onto the original dynamics. Or we can say, oh, I have x sub I of L plus 1 is equal to x sub I of L plus h x of L minus R of L. What were the original dynamics? That was just x of L plus 1 equaling phi x sub L plus gamma U of L. Can I put that into a set of equations? If I had 4 state variables, if x was 4 and x sub I is 1, now I effectively have 5 state variables. I have my original 4 state variables and I have my integrator state. I now have a dynamic system that's 5th order. I've simply introduced one additional state so that I can now put all of those into one vector. How do I fill this in? I now simply need to make this matrix representation consistent with this blue and black. Notice I didn't say black and blue. This blue and black set of equations. X sub I of L plus 1. That's just one row tall. X is 4 rows tall. So I now have a 5 vector. And to be block compatible, I can now partition this into a 2 by 2 block matrix structure where this upper left-hand block is how big dimensionally. How many rows does that upper left-hand block have? How many rows did X sub I of L plus 1 have? 1. And we know these have to be compatible. And I want this top row to actually be the blue equation. How do I pull off X sub I of L in the top row? Do you see that I can get that by just putting a 1 in that 1 by 1? That's now a 1 by 1 submatrix in this 5 by 5 system matrix. This is an augmented system matrix. I've now accounted for this part. How do I create the other two pieces in the top row? Because now I'm going to have this and that. Do I need a U of L piece in this top equation? Not directly, so I can fill this in with a 0. So that was this piece right here. Didn't exist. I still need to put in an R of L piece. How do I put that in? Just with a -1. So now I can pull this in with a -1. How do I get H X of L? I just put in the H right there. Now I've accounted for all of those pieces. My matrix, my augmented system matrix is 5 by 5. The 1 by 1 upper left-hand corner, and then I have the 1 by 4 submatrix that contains the H matrix. How do I create the bottom block structure? Do I have X at time L plus 1 containing any X sub I of L term directly? No. So I actually have a 0 right there. How big is that 0? Is it 1 by 1? Is it 2 by 2? How many rows are in that 0 submatrix? 4. Thank you. Because my state vector was 4 rows tall. That 0 submatrix has to be compatible with X of L plus 1, which is 4 rows. How wide is that 0 submatrix? It's 4 rows tall. How wide is it? It has to be compatible with X sub I. How big was X sub I? 1 row, so the 0 is 0, 0, 0, 0. 4 zeros on top of each other. What's in the 2 by 2 submatrix? Phi. Now I've accounted for this piece. How do I make the next pieces come into play? I need a gamma that scales U, and I don't need an R piece. These are now my augmented system matrices. Phi bar and gamma bar, and what I would do is now I want to control this. The control law If you'll give me one more minute, I'll finish this up. From this block diagram, the control law, oh my, is now minus k sub I x sub I of L minus k hat x of L and now I have a full state feedback gain matrix, maybe a k bar, that I can design. I know how to make a full state feedback gain matrix. I just now, when I have that, I have to partition it such that the very first column is k sub I and the last four are what make up k hat. And that's now my way of designing this integral control design approach with a phi bar, a gamma bar, and an R with this full state feedback gain matrix K bar. You can now ponder that, but that won't necessarily be on the final. The final will be containing the N sub 1, or the reference input, both the regulator, full state feedback, and the tracking with N sub 1. So study up on that. Don't forget homework assignment number 8, and I'll see you, if not before, I'll see you at the final.